All right, let's talk about steel columns. You see them everywhere, holding up buildings, bridges, you name it. But how do engineers actually design them so they don't, fail? Today, we're going to pull back the curtain and demystify that exact process, step by step, for these crucial compression members.
So, here's our game plan. First, we'll get into the #1 danger that columns face. Then, we'll cover the most important first step an engineer takes, classifying the steel section. From there, we'll walk through the actual strength calculations, and finally, we'll tackle the tricky problem of what to do when a section is just too thin, or what we call slender.
Okay, let's dive right in. Before you can design a column to be strong, you have to understand its greatest weakness. Its kryptonite, if you will.
So what do you think it is? I mean, when you picture a column failing, you probably imagine it just getting crushed under a massive weight, like a pancake, right? Well, that's almost never how it actually goes down.
The real enemy here, the thing that keeps engineers up at night, is buckling. This is when a column that's being squeezed suddenly bows out to the side. It's a sudden, kind of violent failure, and it can happen long before the steel itself is even close to its crushing point. Preventing this is job #1.
And to be even more specific, we're often worried about local buckling. So picture an I-beam. It's made of thin steel plates, right? Well, if one of those plates is too thin, it can literally ripple and crumple all by itself, which then causes the entire column to fail way too early. The whole design process is basically a safety check against this one specific problem.
And that brings us perfectly to the first, and I mean the absolute most critical step in the whole process. You have to classify the steel section. Before you can do any fancy math, you have to know exactly what kind of shape you are dealing with. And hey, don't just take my word for it. This is the golden rule. As engineer Mafefe Moloko puts it in our source material, you have to classify the section first. This single step dictates the entire design path you're about to take. There are no shortcuts.
For a typical I section, this whole classification thing boils down to checking 2 key parts. First, you look at the flanges. Those are the top and bottom horizontal bits. And then you check the web. That's the vertical piece connecting them. You got to check both of them.
So how does this actually work? It's really just a simple ratio. For the flange, you calculate how wide it is compared to how thick it is. Then you check that number against a limit set by the engineering code. And that limit, by the way, depends on Fy, which is just the yield strength of the steel, basically how tough the material is. If your ratio is below the limit, awesome. The flange is beefy enough. It passes the check.
Now this brings up a fantastic question that came from Tilayaho Matobela in the source material. Are the rules for this classification different depending on how something is being compressed? The answer is a big yes, and it's a really important distinction to make.
And here's why it matters so much. Columns, what we're talking about, are under axial compression, a straight-down squashing force. For that, we use one set of rules from Table 3 in the code. But beams get compressed in a totally different way. It's called flexural compression, and it happens when they bend. That's a different beast altogether, governed by a different table, Table 4. So for our column design, we're living in the world of Table 3.
Okay, so let's say our section passed with flying colors. It's not slender, it's a good column. Now we can finally get to the main event, calculating how much load this thing can actually handle.
This is basically a 3-step dance. First, you calculate the slenderness ratio for the whole column. Second, you use that number to figure out its theoretical buckling strength, which we call Fe. And finally, you take that Fe value and use it to get the column's real-world design strength, its compressive resistance.
So what on earth is a slenderness ratio? Just think of it as a wobble factor. It's a number that compares how long and skinny the column is to how sturdy its cross-sectional shape is. The higher the slenderness ratio, the wobblier the column is, and the more likely it is to buckle. Simple as that.
And the code is super clear on this. There is a hard limit. If any member has a slenderness ratio over 200, it's just considered too unstable. You can't even use it as a compression member. You have to go back to the drawing board. It's a non-negotiable safety stop. Now, a column can buckle in different directions, right? So here's the crucial part. An engineer has to find the path of least resistance, the weakest link. They calculate the slenderness ratio for each axis, and they use the biggest one to drive the design, because that's the direction it's most likely to fail in. This then leads them to find the buckling strength, or Fe, for each axis, and to be safe, they always use the smallest one. It is all about designing for the absolute worst-case scenario.
But what if we go all the way back to step 1 and our section failed that classification check? What if its flange or its web was just too thin? Well, now we've got ourselves a slender section problem, or what's officially known as a Class 4 member.
A Class 4 member is basically a section that is guaranteed to have that local buckling problem we talked about at the very beginning. Its parts are so thin that they will crumple before the steel can reach its full potential. So that standard design procedure we just went through, yeah, you can't use it because you can't trust the full strength of the section.
So what's the workaround? The solution is actually pretty clever. Since you can't rely on the whole cross-section, you basically just pretend the wobbly bits aren't there. The code makes you calculate a smaller, effective area by mathematically slicing off the parts of the steel that are just going to buckle away anyway.
So the procedure gets a little tweak. First, you pinpoint which part is too thin. Then, you use a special formula to figure out how much of it is ineffective, and you subtract it. That leaves you with your new, smaller, but trustworthy effective area. And from there, you just redo the whole compressive strength calculation, but you plug in this new, smaller area instead of the original one.
Okay, let's bring it all home. What are the key things to remember? Number 1, always classify the section first. That one step tells you which road to take. If your section is not slender, you get to use its full area in your calculations. But if it's a slender Class 4 section, you must calculate and use that smaller, effective area. And remember, the entire point of this careful, deliberate process is to make sure that column is safe from its greatest enemy, buckling.
And this whole process, especially that idea of an effective area, leaves you with a really interesting thought. It's a perfect snapshot of the constant balancing act engineers perform every single day. They have to be efficient with materials to keep costs and weight down, but they can never, ever compromise on safety. It really makes you wonder, where is that perfect, invisible line between getting the most out of your material and guaranteeing it will be absolutely safe?